All right, let's pull back the curtain on one of the biggest marvels in modern tech, computer vision. It really feels like magic, but the truth is something even more elegant. I mean, think about it for a second. You snap a picture of your friends and bam, almost instantly, little boxes pop up around everyone's faces. How on earth does your phone know where to look? What is it actually seeing? Well, the secret isn't some super complex AI that thinks just like a human. Nope. It's actually a powerful and, surprisingly straightforward mathematical process. And today, we're going to break it all down. So to solve this little mystery, we need to look at the technology that's doing all the heavy lifting. Convolutional neural networks, or CNNs for short. And at the very heart of these networks is one core operation that pretty much changes everything. To make this all super simple, I want you to imagine a computer trying to understand an image is kind of like a detective arriving at a crime scene. It's just a jumble of clues, a mess of data. And that detective needs a special tool to find the important patterns. And that tool is called convolution.
So what is convolution really? Well, in simple terms, it's a process where we take a small filter, it's called a kernel, and we just slide it across every single part of an image. And the job of this kernel is to look for one and only one specific type of pattern.
And this brings us right back to our analogy. The image itself is the crime scene, just a grid of pixels with no real meaning yet. The kernel is the detective's specialized magnifying glass, and it's designed to light up only when it finds a very specific clue, like a vertical edge, a certain color, or maybe a particular texture. Okay, so let's get into the nitty-gritty here. How does this search actually work? How does this magnifying glass, this kernel, actually scan the crime scene and report back what it finds? It's a systematic four-step dance, really. First, you place the kernel over a small patch of pixels, let's say in the top left corner. Second, the numbers in that kernel get multiplied by the pixel values that are right underneath them. Third, all those results get added up into one single number. And finally, the kernel just slides over to the next spot and does it all over again, and again, systematically scanning the whole image. So what do you get from all that work? It isn't a new picture. It's something we call a feature map, and you can totally think of it as the detective's clue map. This new grid uses high numbers to shout, hey, the pattern is right here, and low numbers to say, nope, nothing to see here. But, just finding one type of clue, like vertical lines, isn't enough to solve the whole case. The real power of convolution is just how incredibly efficient and clever it is at finding all the clues. So, why is this method so smart? Well, first off, it's super efficient. It uses the same magnifying glass, that same kernel, across the entire image. This little trick is called parameter sharing, and it saves a massive amount of computing power. It also focuses only on small, local patches at a time. And this is huge, because it means the network can find a cat's ear, whether it's in the top left or the bottom right of the photo. The pattern's the same, so who cares where it is? Now, a real neural network doesn't just use one magnifying glass. Oh, no. It uses dozens, sometimes hundreds of them, all at the same time. One kernel is looking for vertical lines, another's looking for horizontal lines, another for green patches, another for curved edges, and all together they create an entire case file of different clue maps for that one image. So let's see how this all builds up from a simple mathematical trick into a technology that is, and I'm not exaggerating, fundamentally changing our world. Because when a computer can truly see, it can do some absolutely incredible things. This one core idea powers so much of our modern world. It's behind simple image classification, telling a cat from a dog. It's what allows self-driving cars to detect pedestrians. It's what enables medical AI to spot tumors in X-rays, sometimes with superhuman accuracy. And get this, it can even be adapted to find patterns in sentences for language processing. It's just that versatile. And it's just incredible to remember that all of these revolutionary applications, from autonomous vehicles to medical breakthroughs, they all boil down to that simple, elegant idea we talked about. Just a tiny detective's magnifying glass sliding over pixels looking for clues. So, our detective is getting very, very good at finding clues and seeing patterns. Which means the question for us now is what mysteries should be pointed toward next? What do we want our machines to truly understand about the world they can now see? Something to think about. Thanks for joining me.